Have you ever gazed at the starry sky and wondered, are we alone in the universe? This question has sparked the curiosity of humans for centuries, leading us to explore the vastness of the celestial realm in search of answers. Please take a moment, hit the like button, and subscribe to our channel for more thought-provoking content. Our universe is a colossal expanse of space, teeming with galaxies beyond number. Each of these galaxies is a cosmic metropolis, a bustling hub of countless stars, around which revolve an unimaginable number of planets. The sheer size of this cosmic landscape is enough to boggle the mind. Given this mind-boggling vastness, the idea that we are the only intelligent life in the universe seems almost absurd, doesn't it? Yet despite our best efforts, we have yet to encounter any evidence of extraterrestrial life. This puzzling situation is known as the Fermi Paradox. Named after physicist Enrico Fermi, it refers to the apparent contradiction between the high probability of extraterrestrial life and the conspicuous lack of evidence or contact with such civilizations. The paradox becomes even more baffling when we consider the age of the universe. It is estimated to be around 14 billion years old, while our Earth is a relatively youthful 4.5 billion years. This means there has been ample time for intelligent life to evolve and develop technology that could reach out into the cosmos. So, the question remains, where is everyone? Why is the universe so silent? It's as if we've arrived at a party only to find that we're the first ones there, or perhaps the only ones there. It's a mystery that has puzzled some of the greatest minds in science. If the universe is so vast and potentially full of life, why haven't we heard from our cosmic neighbors yet? Enter the Drake equation. The Drake equation, proposed by Frank Drake in 1961, attempts to answer this question. Let's dive right into it. The Drake equation is not your typical mathematical formula. It's a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It may sound complicated, but let's break it down into its 7 variables. First, we have the rate of star formation in our galaxy, which gives us an idea of how many stars are being born every year. Then, we factor in the fraction of those stars that have planetary systems. It's like asking, how many of these stars have planets orbiting them? Next comes the number of planets per star that could potentially support life. These are the Goldilocks planets. Not too hot, not too cold, but just right for life as we know it. The fourth variable is the fraction of those planets where life actually develops. This moves us from potential to reality, from could to does. Following this, we consider the fraction of life that evolves into intelligent life. Think about the leap from single-celled organisms to beings capable of understanding and manipulating their environment. The sixth variable is the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. This is about whether they're technologically advanced enough to send out signals that we could pick up. Finally, we consider the length of time for which such civilizations can communicate. This is a sobering reminder of the impermanence of civilizations, including our own. Put all these together, and you get the Drake equation. It's a way of combining our understanding of astronomy, biology, evolution, and technology to make an educated guess about one of the biggest questions in science. Are we alone in the universe? So, the Drake equation gives us a way to estimate the number of civilizations with which we could potentially communicate. Now that we understand the Drake equation, let's delve deeper into its variables. First off, we have the rate of star formation, represented by the letter R. This takes into account the yearly number of stars that are born in our galaxy. Current estimates range from 7 to 15 per year, but this is a tricky number to pin down, with countless variables at play. Next, we have FP, the fraction of those stars that have planetary systems. Thanks to the keen eye of the Kepler Space Telescope, we've found that planets are quite common, with most stars likely having at least one. Then comes Ni, the average number of planets that could potentially support life per star that has planets. This is where things start to get really speculative. We've found planets in the so-called Goldilocks zone, where conditions might be just right for life as we know it, But how many of these planets actually host life is still a big unknown. The next variable, FL, represents the fraction of the above planets where life actually develops. This is perhaps the biggest mystery of them all. Despite our best efforts so far, Earth is the only place we know of where life exists. The variable phi stands for the fraction of planets with life where intelligent life develops. Again, based on our single data point Earth, it's difficult to make an estimate. Next is FC, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. As we've seen with our own civilization, this is not a given. Finally, we have L, the length of time such civilizations release detectable signals. This could range from a few decades to millions of years, depending on a multitude of factors. The Drake equation, then, is not about certainty, but about allowing us to ask the right questions. With each variable, we're invited to explore a new aspect of the cosmos, to probe the mysteries of life, intelligence, and our place in the universe. It's a guide, a roadmap to the stars, and perhaps to finding our galactic neighbors. The Drake equation, then, is not about certainty, but about allowing us to ask the right questions. The Drake equation has profound implications for our understanding of our place in the universe. It's a beacon, guiding us through the cosmic sea, illuminating the potential for other civilizations sharing our galactic neighborhood. Yet, this equation also presents us with a paradox. Enter the Fermi Paradox. Named after physicist Enrico Fermi, it poses a simple yet haunting question. If there are a multitude of extraterrestrial civilizations in our galaxy, why haven't we encountered any clear evidence of their existence? The Drake equation, with its myriad of variables, suggests the existence of numerous civilizations, but the silence from the cosmos tells a different story. This disparity between expectation and observation is where the concept of the Great Filter comes into play. The Great Filter is a hypothetical barrier that life must overcome to persist and evolve into a civilization capable of interstellar communication. The hurdles could range from environmental catastrophes to self-destruction. In essence, the Great Filter poses an existential challenge to civilizations, potentially explaining the deafening silence we've encountered thus far. The implications of the Drake equation extend beyond the Fermi Paradox and the Great Filter. It forces us to consider our own survival. As we plug in numbers and speculate about other civilizations, we inevitably reflect on our own journey. How many filters have we passed? Are there more to come? Could we, as a civilization, navigate these hurdles and ensure our survival? Or are we destined to fall silent like the civilizations the Drake equation suggests may have existed? In the end, the Drake equation does not provide definitive answers, but it does give us a framework to explore one of the most profound questions. Are we alone in the universe? It encourages us to look up at the stars, to question, to wonder, and to continue our search for companionship in the cosmos. After all, the journey of discovery is as important as the destination itself. So, do aliens exist? The Drake equation gives us a way to approach this question scientifically. We've taken a deep dive into the fascinating realm of the Drake equation, a mathematical formula that seeks to estimate the number of active, communicative, extraterrestrial civilizations within our own Milky Way galaxy. It's a tantalizing concept, isn't it? We've dissected the 7 variables that make up the Drake equation, each one representing a different aspect of cosmic existence and evolution that could potentially lead to the development of advanced civilizations. From the rate of star formation, to the fraction of those stars with planetary systems, to the likelihood of life developing on those planets, and even to the probability of that life becoming intelligent and technologically advanced enough to communicate across the cosmic void. We've also discussed the implications of this equation for the Fermi Paradox, the intriguing contradiction between the high probability of extraterrestrial life suggested by the Drake equation and our lack of contact or evidence of such civilizations. It's a paradox that continues to baffle scientists and stoke our collective curiosity. But what does all this mean? Well, it's a reminder that our universe is vast and complex, filled with mysteries we've yet to unravel. It underscores the importance of ongoing scientific exploration and the power of questioning. We may not have definitive answers to whether or not we're alone in the universe, but every question we ask brings us one step closer to understanding our place in the cosmos. Remember, science isn't just about finding answers, it's about asking the right questions. It's about challenging our perceptions and pushing the boundaries of what we know. So keep asking, keep exploring, and keep pushing those boundaries. While we don't have definitive answers yet, the search for extraterrestrial life continues. Until next time, keep looking up and wondering,